Hello everyone, thank you for coming. My name is Eric. I work in Northeastern University, Boston, USA. So the title of this work is Enforcing Non-holonomic Constraints in Aerobat, a roosting flapping wing model. So let's get straight to the introduction. Our lab, Silicon Synapse Laboratories, work primarily in bio-inspired robotics. This work in particular, we're trying to mimic bat flapping dynamics, um, trying to create a robot that can capable of mimicking bat flight. So in this work in particular, we're trying to create a simulation model where we can simulate the bat flapping behavior. Like we're going to model the aerodynamics, and then we're going to perform this upside down perching maneuver, which is something that bat commonly do when they're trying to rest. So we have over here is the past work and motivations. So we're trying to create a bio-inspired robot that mimics bat flapping gait, where the bat flapping gait is highly dynamic and articulated. It has over 40 joints, which generates more than 40 modes of that describe this flapping gait. We obviously cannot mimic all of them, so we generated this design where we mimic two of them, particularly the flapping gait and the wing folding and expansion. So we achieve it by using this kinetic sculpture over here. Like we want achieve through like some 4-bar linkages. So one will be for flapping, and then one this joint correspond to the flexion and elbow flexion and extension. So for the simulation that we're going to do in this work, we also try to capture the two other modes. So total 4 modes. The two other modes being the medial turn movement, which rotates the wing forward, and the feathering angle, which corresponds to the pronation and supination of these joints over here. Next is a quick overview of the password related to upside down perching. So we have developed this landing gear called Harpoon, which works using reaction wheel and to reorient the robot. And then once the robot is oriented, it will launch this landing gear into the landing surface. So this way, like this is what we're going to use in the real robot in order to achieve perching after the robot has turned upside down. Here is the password for flapping wing robots. There are a lot of flapping wing robots out there. So like they can be categorized as non-morphing and morphing wing. Particularly like the non-morphing wing has a fixed wing and like they only have a flapping motion. So a lot of them can be categorized as on the smaller scale side, which is basically micro aerial vehicles. These are flapping wing developed to mimic insect flight. So there's some more medium-sized robots such as Das and Bolt by UC Berkeley, and then there's Robo Raven over here, which has a wingspan of over 1 meter. On the morphing wings side, there are a lot of robots out there. I mentioned earlier about Aerobat over here, and over here is the B2, which is the predecessor of this robot, and then we have the other robots such as from Colorado and all over here. There's a robot Swift. There's a pigeon bot over here, which the wing can expand and retracts. And then there's from the Alderavian over here, which has the wing can bend like this on the elbow, if that's an elbow. And then we have this Diluca, which also has a wing morphing capability, though not as pronounced as the pigeon bot. There's some MIT Phoenix and Smartbird, and this um, interesting robot where it can achieve multimodal where the wing can morph into a leg. So there are a lot of examples of flapping wing robots, and we're currently trying to achieve something on a medium to small scale. So this Aerobat has a wingspan of around 60 to 70 centimeter, and has currently it's estimated to be weighing about like somewhere between 25 to 30 grams. Other past works we have done on the dynamic side of the simulation. So we have the Lagrangian modeling, nonlinear flight control, and trajectory planning done by Ramezani and Hoff. Other past work includes the dynamic modeling of the flapping wing math done by Dickinson, where they characterize the lift and drag coefficient on a small scale insect robot. So we're going to use the same lift and drag coefficient model they have in this simulation of the aerodynamic forces. So here's a quick outline of our presentation. So it's like we'll briefly cover dynamic modeling. which will be very brief because like the full derivations can be seen in the paper itself. And then we're going to move into the gate optimization, which is an open loop gate design that we do to find the zero path flight and upside down perching maneuver. And then we'll finish with conclusion and future works. So the summary of the dynamic modeling is that we're using Euler-Rajendran dynamic modeling. So the system has 14 degrees of freedom. So the body has a full 6 degrees of freedom. And then like we have these four joints, two on each wings. So these four joints are can only rotate in two directions on each of them. So it's like on the shoulder joint, we have plunging motion, which goes up and down, medial lateral movement, which rotates the wing forward, and then we have the elbow joints over here, and then we have this what we call feathering angle, which creates the subpronation and supination of this wing surface. So the wing surface itself is modeled as a simple plate like this, and it's done to simplify the aerodynamics calculations later. So the wing surface, as mentioned earlier, is composed of this simple plate over here. So because of the way flapping works, like each of these wing surface have different effective airspeed acting on it. So we have to integrate the aerodynamic forces across this wing plate. We have both span-wise and chord-wise integration. So in this case, like we integrate about the span and the surface about the chord, and then the force itself is applied like a quarter chord away from the leading edge. We also do another integration here, like across the span, because like there's a possibility of this edge to be leading edge as well, due to how the flapping works. So this is done to take that into account. So the lift and drag coefficient is taken from Dickinson, as I mentioned earlier. So after we derive the model, we try to find a gate where we have a limit cycle where the robot's just flapping in place. So we offer a very simple trajectory here, which is just sinusoid trajectory. So it has amplitude, mean angles, and phase difference of four joint angles relative to the plunging angle. So this is the four angles that I mentioned earlier: plunge, medial, lateral, elbow, and feathering. And we try to minimize angular momentum and vertical velocity using some standard optimization technique. So the resulting optimized trajectories is shown over here, which I'll show the animation after this slide. So here's the simulation results using the dynamic modeling and optimization described earlier. So you can see the simulation animation on the left and the plots on the right side. The robot is under a 2 meter per second wind speed acting from the front side of the robot, and we're simulating this using 10 Hertz flapping frequency, which is typical for bats of this size. And we have a limit cycle after 0.5 seconds, which it goes to a pitch angle of about 50 degrees. You can see it on the left over here. So it's kind of there's this upright and almost horizontal flapping angle. Flapping trajectory is something that you typically see in hovering birds like hummingbird. Here are the keyframes from the animation in the previous slide. This is done to show that we have captured the four modes that described earlier. So we have the plunging motion over here, which move the wing up and down, which from the core flapping gate. Then we have these elbow joints, flexion and extension over here, which retract and expand the wing. During the upstroke, the wing is retracted to minimize the wing surface and also minimize negative lift. So next is the feathering, which pronates and supinates the elbow joint, which has the effect of changing the angle of attack. Then finally, we have the medial lateral mode, which where the wing swings forward. As you can see, like that zero path flight gate has all four modes, and this creates a stable limit cycle. So next, we're going to talk about the upside down perching. So we have this. We simply add an offset to the stable grade trajectory found earlier, which is equal and opposite between the left and right wing. This causes some imbalances, which creates the force imbalance on the aerodynamic forces, which will help the robot to roll. So we have this bump, which is the offset will be this bump over here, and then we want to minimize tracking error to this 180 degrees trajectory for the body roll angles. Here is a simulation result of the animation upside down perching. You can see the front view over here, isometric view over here. So the upside down perching is done by tucking the one wing underneath the belly and the other wing extend upwards and also pronates. So you can see it more clearly on this body fixed front view. So one wing gone under the belly and the other wing pronates. You can see it over here, and it achieves this rolling motion shown on the left. So the optimization results can be shown over here. Like the values we use for the upside down maneuver is primarily just the plunge and feathering angles, which seems like those two angles are enough to achieve this result. So we have the body turning upside down 180 degrees through the roll angle, as you can see over here. And the angular velocity indicates that the robot is slowly becoming unstable after it's turning upside down. So we hope that our latching mechanism has successfully latched into something as soon as the robot turns upside down, because this seems to be going unstable afterwards. So to summarize, this upside down maneuver can be achieved by tucking one wings under the belly and the opposite wing extends upwards and also pronates, and that's results in this upside down maneuver seen here. So in conclusions, we have developed a simulation model for the flat flapping gate, including the aerodynamics, and we have successfully found an open loop gate for a zero pad flight and upside down maneuver. So for the future work, we can implement a feedback driven components onto the robot to maybe stabilize the pitch, which seems to be always pitching upwards. And then we can also try a closed loop controller to stabilize the orientation and altitude of the robot. And then we have to test this on the actual robot that we're currently building. That's all for this presentation. Thank you for listening and have a good day.